Hello everyone, I'm Mohammadreza Bayatpour. I'm a PhD candidate at the Ohio State University. Today, I would like to talk about our research on communication-aware hardware-assisted MPI overlap engine. This is the agenda for today's talk. So first we talk about some introduction, then we will talk about some background related to our research, then we will talk about the proposed designs, followed by experimental results and conclusion. Current trend in the modern HPC architectures are in a way that processors are having more and more core inside the same node. Also, high-performance interconnects such as InfiniBand and OmniPath are having more bandwidth, and also they are getting equipped with high-performance in-network capabilities such as sharp and hardware tag matching. Modern supercomputing systems such as Samidor, they are also equipped with GPUs and coprocessors, as well as high-performance storage systems such as SSD and NVMe and NVRAM. There are several pair programming models, such as shared memory model, distributed memory model, and partition global address space or PGAS. These models provide abstract machine models that can be mapped on different types of systems. MPI is actually a de facto model for writing parallel applications, and in our research we are focusing on MPI. This model offers various communication primitives such as point-to-point operations and collective operations, as well as RMA operations. Now I want to talk about some background. So first we'll talk about MPI tag matching. Then we will talk about some of the protocols in MPI for implementing point-to-point operations, such as eager and rendezvous. Then after that, we will talk about hardware tag matching in EDR and HDR. So what is MPI tag matching? MPI tag matching is an operation which takes place at the receiver side. So basically, whenever an incoming message is received, receiver side has to perform some source of tag matching upon the incoming message, so that it can realize the incoming message is related to which of the pre-posted received requests, so that data can be appropriately placed into the receiver buffer. So as you can see here in this figure, we are simplifying the stacks of MPI stack, and as you can see here, tag matching is inside the critical path of every point-to-point operations, and collective operation as well as RMA operation can also be implemented on top of point-to-point operation. Therefore, we can see that tag matching has a big impact on the performance of the MPI. So here I would like to talk about eager protocol. This protocol is mostly used for small messages, and this protocol basically uses pre-registered buffers for communication. So as you can see in this diagram, first the data is copied to temporary buffers in the MPI library. These buffers are registered with HCA. Then we have the network transfer. Then at the receiver side also there is a copy from the temporary buffer to the application buffer. Another protocol is Rendezvous Protocol. So this protocol does not have copy operations of the real application data as we saw in eager protocol. However, it has some overheads for handshaking. So basically the sender sends the RTS message, then receiver sends back the CTS message. Then we have the RDMA read or write, and here in this example we have RDMA write, and at the end we will have the FIN packet. As you can see, there are several costs regarding this protocol. Now, so far we have talked about the performance aspects of the eager and rendezvous protocol. Here we would like to talk about the overlap of communication and computation in both of these protocols. So on the left hand side, I'm talking about the eager protocol. So here we have three colors, green, red, and gray. In the green area, processes are performing useful application computations. On the red areas, network is transferring the actual data. And on the gray area, main process is inside the MPI library, which means that it can progress the communication. So in the eager protocol, since there is no handshake, the data transfer can be initiated as soon as the MPI send is posted. As you can see here, there is overlap of communication and computation. However, on the Rendezvous protocol, on the right-hand side of this figure, we can see that since there is handshaking, as in this figure, since the receiver side, when the RTS is received, main process is performing the useful application computation, and assuming that there is no asynchronous progress thread here, main process does not realize that actually it has received the RTS message. Therefore, it cannot send back the CTS message early enough. Therefore, we can see that there is no overlap of communication and computation here because of the requirements of the synchronization. So now we would like to talk about the hardware tag matching. This feature has been recently added to the InfiniBand Connect X5 and 6 models. So basically, the offloading the processing of MPI tag matching is offloaded from host to the HCA. So it has multiple benefits. So one of the benefits is that basically the eager protocol can be implemented inside the HCA. So which means that as we are showing in this figure, on the left hand side, I'm showing the eager protocol just like we discussed before. However, on the right hand side, we can see the eager protocol using hardware tag matching. So the main difference is at the receiver side. Since receiver HCA can perform MPI tag matching, it knows where the receiver buffer is. Therefore, it can perform tag matching and directly places the data in the receiver buffer. However, on the left-hand side, in the regular manner, we have one extra copy overhead. Now, I would like to talk about the Rendezvous protocol using hardware tag matching. So on the left-hand side, I'm showing the CPU-based Rendezvous protocol, which is similar to what we discussed before. So here you can see that RTS is sent. Then since here application is doing computation, it can just perform the RDMA read whenever it goes inside the MPI init. Sorry, MPI wait. And then it can sense the feed. On the right-hand side, I'm showing the same procedure using hardware tag matching. So using hardware tag matching, even though the receiver side is performing computation, still HCA can perform tag matching and appropriately perform RDMA read whenever there is a match, and then send the feed. As you can see here, there is full overlap of communication and computation, even for Rendezvous protocol. Now, with all of these backgrounds in mind, we come across this broad challenge that how can we design an overlap engine which is capable of adaptively utilizing advanced hardware and software-based schemes for progressing MPI operations for diverse application and communication scenarios, which can be more detailed in these several bullet points, such as what are the performance characteristics, benefits, and shortcomings of state-of-the-art hardware tag matching and offload? Are the capabilities provided by hardware sufficient, or do they need to be augmented by software schemes? Another question is that which communication scenarios can be improved in terms of performance and overlap by offloading to hardware? And can we propose novel designs to extract overlap for unexpected messages? Can it be done without increasing the footprints of MPI library? And lastly, can the proposed designs be combined so that they can be adaptively applied to the application's communication requirements. So here we would like to talk about the motivations for this research. So from our previous work in CC Grid 20, we have realized several shortcomings for Harvard tag matching. One of the shortcomings is related to performance challenges. So as I'm showing here in this figure, you can see that bandwidth of the offloaded receive requests are lower than the CPU-based receive request handling. Another challenge is semantic challenges. So basically, Harvard tag matching mandates that no offloaded and unloaded receive requests exist at the same time with the same tag. Otherwise, it will lead to data invalidation. So in order to measure this behavior, we have made a synthetic benchmark, as we can see the figure on the bottom. So this benchmark is basically based on OSU bandwidth test, where we measure the overlap instead of bandwidth. Also, another difference is that we are inserting one non-contiguous data type inside the window. So window means that, for instance, when we say window size is 64, it means that we have 64 concurrent MPI receive. So here, for instance, but please note that non-contiguous data types are not currently supported by Harvard tag matching. Therefore, they cannot be offloaded. Contiguous data, on the other hand, can be offloaded. Therefore, here we can see that one of the elements in the window is non-contiguous. So index 0 means that the first element is non-contiguous. Element 63 means that the last one is non-contiguous. Therefore, all the receive requests before the non-contiguous data type can be offloaded, and whatever which is posted after that is not possible to get offloaded because of this semantic challenge. As we can see here, the one which is posted at the beginning is giving the lowest overlap, and the one which is posted at the end of the window is having the highest overlap, because basically if the window size is 64, the 63 of the receive requests are offloaded, and only the last one is not getting offloaded. Therefore, we can see close to 100% overlap of communication and computation. So it is important because a lot of applications can have a mixture of contiguous and non-contiguous data types, and also because of some performance challenges, sometimes we don't want to offload some of the received requests. Therefore, in order to maximize the utilization of Harvard tag matching, we need to take care of this challenge as well. The last challenge we would like to talk about is unexpected messages. Basically, as we discussed before, receiver side needs to know the tag as well as the buffer address of the posted receive request in order to be able to take care of the incoming message. Otherwise, if the message is unexpected, it should be handled by the CPU. Now we would like to talk about our proposed design. So basically, since we have three challenges, we have three different designs. One for expected messages, which is basically tries to minimize the bandwidth overhead. Another one is a trace-based matching design, where it tries to increase the resource utilization. And the last one is regarding unexpected messages in order to provide more overlap of communication and computation. All of our designs has been implemented in the popular MVAPIsh2 library. MVAPIsh2 is a very popular MPI library across the world, and it has been used in many modern supercomputer systems. So here we would like to briefly talk about the first design for expected messages. So the basic idea behind this design is that we would like to only offload the receive request when we expect to see benefit by offloading it. which means that we expect to see overlap of communication and computation. So here, for instance, on the left-hand side, there is no overlap of communication and computation. Sorry, on the left-hand side, since the receiver side progresses the communication frequently enough, there is no need for hardware tag matching because already there is enough communication progress happening at the receiver side. Therefore, when the RTS is received, receiver side can quickly respond to it and issue RDMA read. And therefore, it can avoid the bandwidth issue of the offloaded receive request. However, on the right-hand side, offload is actually helpful because the receiver side does not progress the communication frequently enough. Therefore, if we offload the receive request to the HCA, as soon as the RCS is received, it can perform RDMA. Even though the bandwidth is lower, but it is expected to see benefit in total execution time because of the increased overlap of communication. So our design has shown benefit compared to all other designs, such as UCX with tag matching enabled in terms of bandwidth, and at the same time, it can also provide the peak overlap of communication and computation. Another design is basically a design which tries to make sure that no two point-to-point operations are having the same tag. This is required because if we have these scenarios, then we can take care of the semantic challenges of hardware tag matching, which means that even if you have a mixture of contiguous and non-contiguous data, then we still all the contiguous receive requests can be offloaded to the hardware. So here we are having the same benchmark that we talked in the limitation or motivation slide. However, with the fact that here index is 0, and basically the first element of the window is non-contiguous data type. As you can see here, even UCX with tag matching enabled cannot take advantage of hardware tag matching because of the semantical challenges. However, our design can still offload the receive request to the HCA and guarantee the peak overlap of communication and computation, as well as the lowest total execution time. And the last design that we would like to talk about here is about unexpected messages. So the basic idea here is that we would like to prefetch the post and incoming RTS and prefetch the data from the sender so that the sender's process can proceed and continue without getting stuck for a delayed receiver process. So to clarify, you can take a look at this figure. So on the left-hand side, I'm showing the rendezvous target, however, in the unexpected manner. So basically, which means that the sender process has posted the send, but at this point, the receiver process has not yet posted the receive request. Therefore, sender process is getting stuck here because of the delayed receiver side. On the other hand, our design tries to adaptively observe the communication pattern of the application and predict whether or not the prefetch is going to be helpful here or not. Therefore, as soon as the RTS is received, it decides to perform a prefetch and send back the FIN packet so that the sender side can proceed. So in order to measure this impact, we have modified the OSU bandwidth benchmark so that can measure the overlap. Latency here is total execution latency. So basically here, as we can see here, in order to make sure that all the messages are unexpected, we have Yeah, we have added artificial delays at the receiver side so that all the messages become unexpected. As we can see here, compared to all other designs, our design is having the highest overlap of communication and computation, as well as the lowest total latency. So we use two different clusters for our experiments: Frontier cluster at the Texas Advanced Computing Center and the Pitzer cluster at the Ohio Supercomputing Center. We also compared our design with NVAPIH 2X version 2.3 RC2 and OpenMPI with the UCX enabled version 4 and UCX 1.4. So the first operation that we would like to talk about is the 3D and stencil operations. So here, as you can see, we ran this benchmark on 128 nodes with one process per node, and our design is able to achieve the lowest total execution time and highest overlap of communication and computation. Another point that we would like to talk about here is about collective operations. So our evaluation showed that if we run OSU micro benchmarks for collective operations, since all the processes are sync, and which means that all the processes enter the collective at the same time, we don't expect to see a major performance boost using the proposed prefetch design. However, if we modify this benchmark slightly to add some artificial delays for some processes, we can see that our prefetch-based design can achieve the best performance compared to all other designs. We also ran some scientific applications such as PTR-TFFT and LAM-MPS to measure the impacts of our design. So for PTR-TFFT, we have observed up to 20 performance improvements in communication, as well as a 3.58 improvement in total execution time of the LAM-MPS. So in this research, we have designed a communication over hardware tag matching offload mechanism. And we have proposed 3 different designs. So we have increased the resource utilization of the hardware tag matching through the trace-based matching. We have proposed novel communication over designs to minimize the bandwidth overhead of the hardware tag matching, and we have proposed novel designs to extract overlap from unexpected received messages through efficient prefetching. We have done a thorough evaluation of the proposed design using various benchmarks and application kernels. So in the future, we are planning to explore the hardware tag matching, and we would like to also bring the support of the hardware tag matching for DC protocol in human. To this end, I would like to thank all of you for listening to my talk. I would be more than happy to listen to your comments, and we can discuss anytime that you would like. Please feel free to send me an email and we can discuss further. Thank you very much.